Today our goal is to deal with the angles we get. From the sigma and pi bonding, we could figure out that the molecule is going to be flat if it had one pi bond, because the pi bond was above and below. And the molecule is going to be a line if it was two pi bonds. One pi bond in the front, one top and bottom, one left and right, and that forces it. The only way you can bond is in a line. Okay? So we've already dealt with that. And that deals with our 180 degrees. Okay? But how do we get 120 degrees? How do we get 109.5? Where are the electrons that give us the 120 and the 109.5? Okay? The answer to that is in hybrid orbitals. Okay? What's a hybrid car? What makes a car a hybrid? Got both gas and electric. Got two ways to move. Okay? So it's got some of the parts of some of the components of an electric car, some of the components of a gasoline engine. When you talked about hybrids last year, it was where you took all dominant and all recessive and crossed them. You had parts of each. Okay? So hybrid orbitals is we're going to put orbitals together and come up with parts of each. Okay? So hybridization is what happens as the atom starts to make bonds. Its atomic orbitals have to change. And they change from being the S's and the P's, because we're only talking about valence electrons right now, to new orbitals. Those new orbitals are going to be hybrid orbitals with some of the components of S and some of the components of P. Now, when we're talking about mixing, it's a mathematical mixing. And it's a mathematical mixing that comes up with the same number of hybrid orbitals. So if I put together 4 orbitals, I have to make 4 new orbitals. If I put together 3 orbitals, I got to make 3 new orbitals. That's what they mean by the same number of hybrid orbitals. So I'm going to blend the S's and P's to come up with hybrid orbitals. Those hybrid orbitals I make are all the same as each other. The only difference is direction. Okay. The name of the hybrid orbitals is the recipe for the hybrid orbital. The name is the recipe. So the first kind of hybrid orbital is called an sp3. It's called sp3 because you're putting together one s and all 3 p orbitals. Okay. Since I put together 4 orbitals, I get 4 new orbitals. And those new orbitals, their only difference is going to be direction. The next recipe is sp2. So the recipe says I put together 1 s and 2 of the p orbitals, 2 out of the 3. And the third p orbital is used for something else. It doesn't get put into the hybrid, it's used for something else. Okay, there's one more. Anybody guess? Can anybody guess what it's called? SP, and the recipe is going to be 1s and 1p. And since I put together 1 and 1, I'm only going to make 2 new orbitals, but I'm still going to have 2 p orbitals left. I always need 8 places to put electrons. So I always have those 4 orbitals available to me. I'm just going to blend them and make different types of orbitals out of them. Okay, so first hybridization we're going to use to explain 109.5. How do you make 109.5 degrees with just S and P orbitals? S's are spheres; they can be any direction. P's are, I think, called dumbbells, but they had to be at 90 degrees from each other. That doesn't explain 109.5. Okay. Well, which ones make, why would I need 109.5? Well, I need 109.5 if 4 pairs of electrons are trying to get away from each other, right? I need 4 orbitals. I either have 4 single bonds, or 3 singles and a lone pair, or 2 singles and 2 lone pair. I need 4 places to put electrons. Okay? So 4 orbitals, which recipe do I need? Which recipe makes 4 orbitals? sp3 makes 4 orbitals, so I'm going to put together my 1s and my 3 p's. To make my sp3 hybrid. So what this tells us is these are the same kinds of decisions I made when I was determining shape. Okay? We are not making new decisions. We're just going to put a new label on that decision. The shape one was about where the atoms were. The hybridization is where the electrons are. See the difference between those two? But it's the same decision. Why would I pick 109.5? Because I got 4 pairs of electrons trying to get away from each other. Why do I pick sp3? Because I got 4 pairs of electrons who want to get away from each other. That's why we do it. It's the same decision, different label. The electrons are going to have to be sp3. So anytime you have that tetrahedral molecular electronic geometry, remember from the simulation they told you electron geometry and molecular geometry, and the two disagreed, okay? The sp3 is about the electron geometry part of it. So here's what the orbitals look like before. When I do the mathematical averaging, I have to have something that's going to be 3-dimensional because the P goes up and down, left and right, forward and back, right? So it's got a 3-dimensional nature to it. So I'm going to have a 3-dimensional nature to my 4 new ones. And that's the 3-dimensional nature of it. It looks like a lobe on one end with a small lobe underneath. Okay? And you notice the first one is straight up and down. All the other ones tend downward, so I have an average of them canceling out, like they would with the p orbitals. Everything would cancel out top and bottom. So those 3 are a little bit down. Okay? And they have to go at 3 different angles around the xy plane and spread around there too. Okay? So when we write something simple like CH4, we write this. We would say that this has 3 sigma bonds, right? Between the C's, 4 sigma bonds between the C's and the H's, right? So that means the C's and H's are overlapping with those sp3 hybrid orbitals. So this is what's really going on. Okay, the red one's the carbon. The sp3s are at the corners of that tetrahedral. So I'm going to get an overlap here, a sigma bond. I'm going to get an overlap here, a sigma bond. Here, a sigma bond, and there, a sigma bond. Okay, so my shape is tetrahedral. That's what we would have said based on VSEPR. And my electrons have to be sp3 because I need 4 places to put electrons.
Wait, so why is the carbon like?
Well, the carbon, that's one carbon, that's where its outside electrons are. Its outside electrons have changed from being S's and P's to being sp3s. When it makes that bond, so they've changed. So every time you have sp3 geometry, you got tetrahedral. Tetrahedral is sp3. Trigonal pyramidal is sp3 because it's 3 atoms and 1 lone pair. Bent at 109.5 is sp3. So anytime you've got a total of 4 atoms and lone pair, it's sp3. Anytime you need 4 places to put electrons, you need an s and 3 p's. Because an orbital is a place to find electrons. So it's not a new decision, a new label on the same decision. On our big blue table, every one that said 109.5, we could have made a column that said hybridization, it's sp3. So that's going to give us trigonal pyramidal and one of the bent at 109.5. We still haven't discussed the 120 yet. So really, if the geometry requires a 109.5 degree bond, it's sp3. If it's sp3, you're going to have a 109.5 degree bond. So when we're talking about shape, we're focusing on where the atoms are at. We're talking about hybridization, we're focusing on where the electrons in the bonds are at. So tonight's homework, which I forgot to write up there. Ooh, good thing I was sitting here. Tonight's homework is going to ask you what hybridization is. So which of those would be sp3 hybridized? Hey. So it's going to be sp3. To me, that means I need 4 places to put electrons. Need 4 pairs of electrons around the central atom. This one only has 3. This one only has 2. This one has 4. This one has 3. So the answer is C. So, and it is the same decision, right? It's, if I ask you which one of these was tetrahedral, the only one that would be tetrahedral up there is C. So it's not a new decision. Hey, that's sp3 hybridization. sp3 hybridization explains 109.5. sp2 hybridization. Okay. And my model for this is going to be C2H2. Have you draw the structure of C2H2. Oh, sorry, C2H4, sorry, C2H4. Sorry, H4. Okay. So carbon wants to make 4 bonds. Hydrogen wants to make 1. The only way it fits together is with a double bond. In. So, remember the double bond counts as 1 pair of electrons. So if I look at the shape of this part right here is trigonal-planar. This part right here, trigonal-planar. So I got 2 trigonal-planar sections hooked to each other. So once again, the question comes, pick the right one, there it is. Which one is it? I got 2 trigonal planars. So here's 1 trigonal planar section. And put these hydrogens in. And there's the other trigonal planar section. So the question is it like this, or like this, or like this, or does it matter? Okay. So we got 2 trigonal planar sections. Okay, so I got to end up with 3 blended orbitals. Every one of these sticks needs an orbital. So I need 3 blended orbitals. So my recipe says I need 1 s and 2 p's, right? So I use 1 s and 2 p's to make sp2 orbitals. But I still need 4 places to put electrons. sp2 is only 3 places to put electrons. I've got 1 p orbital left over. Where is it? Okay, well, let's think about it. I blended 3 orbitals, but we know that it's trigonal planar, right? So the p orbital I didn't use was the one that had up and down in it. This doesn't have an up and down component, so I didn't try to average the up and down like I did with the first one by putting 1 up and 3 down, trying to average out that up and down. I don't have to worry about averaging up because I didn't use the up and down component. So the part I left off, p orbital I left off, is perpendicular to the ones that I used. Okay, so I didn't use this p orbital, so it's still sitting there, ready for 2 electrons. How I went was from pictures. I talked about it, but here's what the pictures look like. I put together 3 pieces, an S and 2 S and 2 p's. I picked the p that went along the x-axis and along the y-axis. Left off the one on the z-axis. I left off the one. I didn't hybridize the one that goes up and down. So that when I make it, all my shapes, my 3 shapes, all go along the xy plane. There's not 1 up and 3 down, not 1 up and 2 down. They're all right on the plane. Everybody see how they're on the plane? So that's where it has a place to make sigma bonds. And hey, notice I got 3 things spread around a circle. What angle is that going to give me? That's going to give me 120 degrees. Okay, let's go back up. I actually, oops, that's not where I want to be. Okay, I looked here at this carbon. It had 1, 2, 3 atoms, no lone pair. So it's 3 atoms means it's got to be a triangle. Without a lone pair, it's flat. That makes sense? So I went through that step by step, and the other one was just like that. 3 atoms, no lone pair, it's got to be flat. Okay. So this blue one is the green ones are the sp2 hybrid orbitals. The blue one is the p I haven't used yet. Okay? So the p orbital was perpendicular, and it's perpendicular on the next one too. Oops, I couldn't afford to break that one. Oh well. All right, so it's perpendicular on this one too. Everybody okay with this? Look at what that puts them. Puts them right next to each other, so they can make a pi bond. So the overlap of orbitals, my sticks are sigma bonds. The sticks represent the sigma bonds where they overlap. Yeah. And so the sigma bond between the atoms, and then I've got the pi bond above and below. So not only is this two trigonal planars, they're two trigonal planars that have to stay flat. This has got to be a flat molecule. And flat is dangerous for molecules. Dangerous? Well, because if it's a big flat molecule, you can get in between the strands of DNA and make it so it doesn't copy the way it's supposed to. Okay? So when you go to the gas station, there's a big warning on it about benzene. Benzene is a flat 6-carbon ring. In fact, it's to the point now where when they're testing drugs, or before they even make the drug, they let the computer figure out what shape it's going to be for big molecules, figure out what shape it's going to be, and look for big flat spaces, because that tells them it's probably going to be dangerous. And we probably don't want to use that as a drug. Okay. So I got two types of bonds. The stick makes the sigma. Those leftover p orbitals make the pi bonds. So when we draw this, it's really closer to that, where my single bonds are sigma bonds, and my double, stay. So my got sigma, 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 sigma bonds where they overlap. There's the 5 single bonds. And then this area right here, those two areas together are the double bond. There's 2 electrons someplace here. That doesn't mean there's one here and one here. Could be both here. Could move from here to here without ever being in between those two places. Because it's a wave. Okay, so anytime you have 3 things come off an atom, anytime you'd say trigonal planar or bent at 120 degrees, it's not a new decision. Now we have another way. In order to make sp2, I have to use a p orbital for something else. And the other thing I use p orbitals for is pi bonds. So it's going to have 1 pi bond. So if your central atom has 1 double bond, you know it's sp2 hybridized, because it only has 2 p orbitals left to blend in. You use the first p orbital to make a pi bond. The other 2, it can blend. Okay, what about 2? When 2 things come off? That means I need 2 orbitals. Okay, so if I only need 2 orbitals, I put together an s and a p. Okay, if I put together that s and the p, notice it doesn't have any up and down component. It doesn't have any front and back component. So they're just pointed in opposite directions along the xy line, the x-line, right? So those 2 ends are going to be 180 degrees apart. Okay, so remember, I didn't use the p orbital that did this, so there's no up and down. I didn't use the p orbital that did that, there's no front and back, so it only blends along the x-axis. I'm not trying to blend up and down. Don't have to divide that up. I'm not trying to blend left and right. No, just. Oh, well, it does, well, we don't know which axis. It's still a line. It's all, yeah, because it's always just one of the p orbitals. So you can only go left and right when you're averaging those. Okay, with that? Okay. So two lobes 180 degrees apart. 180 degrees, we used that when we said things were a line. Okay. Said I didn't use the p orbital. If I didn't use it, I didn't use it to hybridize. But I used it for other stuff. I still got to have 4 pairs of electrons. Okay. And where are the 2 p orbitals? They're perpendicular to the one I just drew. It's the up and down and the front and back. The blue ones here. Those are the 2 p orbitals I didn't use yet. So that means I can overlap on the s and p's. And I can make a pi bond with the up and down. And I can make another pi bond with the front and back. So I got room for 2 sigmas and 2 pi bonds, one up and down, one front and back. So to be to the part where we only have 1 p orbital left, I must have made 2 pi bonds. So I must have made either 2 double bonds or a triple bond. Keep going. Okay, so we look at CO2. We've drawn CO2 a bunch of times. Okay, but let's think about what the carbon's like. Okay, the carbon has 2 atoms and no lone pair. The carbon has made 2 pi bonds. So the carbon has to be sp hybridized. That in one side of the carbon it's bonded to a carbon, on the other side the sp has got the lone pair. Okay. the oxygens. Look at the oxygen, it's made one pi bond. Or you look at the oxygen, it's got 3 pairs of electrons it has to deal with. So it needs 3 places to put electrons. 3 places to put electrons, sp, s, and 2 p's. Or I've used one, so the oxygen looks like that. Got a p orbital we haven't used yet because I got to make a pi bond. And I only have 3 left, sp2. So either by how many pieces are attached, we get to sp2, or by how many pi bonds we've got sp2. Okay? So when you stick them all together, this is how they're hanging on to each other. A single, that's those 2 electrons. Okay? Does that make sense? One of those is in between, the other one is top and bottom. Over here, there's a single and double, that's these 2 electrons. These 2 pairs of electrons. And out here is where the lone pairs are sticking. Notice that on this one, they're sticking on this plane. On the other one, they're vertical because that pi has to be at 90 degrees. It's got to be a 90-degree twist. Is that right? Yeah. So what about something simple like N2, nitrogen? Okay. Well, N2, N wants to make 3 bonds. So the only way N can make 3 bonds, it's triple bonded. I'd have to fill these up, another pair of electrons. Let's double check. Nitrogen has 7. 2 times 7 is 14. I should have 14 dots up there. No, nitrogen has 5 valence electrons. It is number 7. It's got 5 valence electrons. 2 times 5 is 10. Should have 10 electrons up there. That's better. So there's not 14 there. Yeah. So that tells us that those 3 bonds, one of them is a sigma. The second one's a pi. The third one's another pi. So N2 is really sigma, pi, pi. Okay. So, oops, one more. Which were those? Two ways of looking at it. You can either look at it as it's sp, I need 2 places to put electrons, or it's sp, I've got 2 p orbitals I haven't used yet. That means I get to make 2 pi bonds. So either way you look at it, I just need 2 places to put electrons, or I have 2 p orbitals. It's got to be b. It's got to be B because it's just 2 places. So in summary, yep, 3 bonds, yeah. Had to be B. So hybridization. If the hybridization is sp3, what types of bonds are you going to have? So they're going to be all single. Another way of looking at it, they're going to be all sigma. All single bonds, they're all sigma bonds. And the bond angle is going to be 109.5. If it's sp2, for me, the easiest one to answer is sp2. I left off a p. I'm going to make a pi bond. Right? If I haven't used one of the p's for hybridization, I'm going to use it to make a pi bond. That's why they call them pi bonds, is because only p's can make them. Okay. So the other way of looking at one pi bond would be one double bond. The rest all single. And we've got three things coming off. The farthest three can get away from each other is 120 degrees. And finally, SP. Yeah, so I got to use two p orbitals up. So I'm going to make two pi's. So I've got to make a triple or two doubles. I've got to make two pi. The rest are going to be sigma. If they're not sigma, they're lone pair. You understand that lone pair would take the place of one of those sigma bonds. And your bond angle is going to be 180 degrees. Let's see if this is going to work. Okay. Just want water going here. I just need some hot water. Just went and boiled some water in the back room, so I did. Okay, so that's what your homework tonight is going to have you do. Okay. But I should probably tell you what your homework tonight's going to be. That would be nice, wouldn't it? I've written it down 3 times. It's on School Loop, but it is page 193, 3 and 4. Page 197, 196, 23, 25, 51, 61, 67, 68. And so I've got the stuff set up here. So while I've got it set up, I wanted to show you one of the things you read about last night. Okay.